Always a great pleasure to be back to Tata Institute, and I will be talking about a proposal for a definition of quantum gravity using time-like Liouville theory in 2 dimensions. This is work done in collaboration with my former students, Bautista, Arbin, and Kuderna. I mean, he was kind of co-advised. So, okay, Teresa and Harold, they were here actually. They spent some time here, and Kuderna is at Prague. He's a student of. He's a student there primarily, but he did some work with me. So one of the main motivation is that it's a well-known fact that Euclidean quantum gravity how to define the path integral of Euclidean quantum gravity has been a long-standing problem, because, or how to even give a definition of it, because the conformal factor has a wrong sign, kinetic term. So therefore, normally what you do is that you have a path integral. If you go to Euclidean space, it's a Gaussian integral with a damped Gaussian, so the path integral is well defined. Here, it's not clear how to do it. If you have a cosmological constant, then some kind of analytic continuation typically makes the action imaginary, is not real. So then once again, it's not clear how to define the path integral. And this has a number of motivations. One is, of course, that we have been doing some localizations in ADS2, ADS4, etc., using the path integral of gravity. And okay, since we use localization there, you sort of know how to define the path integral at the end of the localization. But the starting point is always a bit ill-defined. So path integral in the bulk. Then another motivation is some of the 2D models of cosmology that I had talked about here earlier. And even from that point of view, you would like to have some starting point where the path integral is well defined. And then there are many statistical models which. So CFT people have been interested in time-like Liouville from another point of view, Potts model and so on. So I think making in certain some of the models that people have studied in which are not unitary. There's a non-unitary, the weights which are non-local and so on. But there are interesting statistical mechanical models where time-like Liouville theory appears naturally.
Is it just that it's C greater than 26 or something in the sign of the Polyakov term changes sign? Or?
No, so they are not doing quantum gravity. It's just a statistical model. But so it has been studied a lot, generalized minimal models, this whole, there's a huge literature on this subject from the statistical mechanics point of view. So time-like Liouville is actually by itself is a very interesting conformal field theory to try to understand. And making connection with quantum gravity is another interesting. So these are the 2 motivations that so let me remind you a bit about the Liouville theory. So I will have to go, I will give kind of an impressionistic summary also, so that the link, even if it breaks down, you will at least know the conclusions. So Liouville theory arises in quantizing 2D gravity. And I don't know how many of you remember this, but basically it comes from the Polyakov the Weil anomaly. That typically if you are trying to quantize some theory, say in 2 dimensions, imagining a quantum gravity, then this path integral measure is defined with respect to this metric g. But in 2 dimensions, you can always write g is equal to e to the 2 phi h by doing some coordinate transformation. And then this action is invariant if the action is in 2 dimensions, this is invariant. But there is an anomaly because the measure requires a definition, the definition of the measure requires the metric. And then using the fact that dx of h e to the 2 phi is equal to, and since it's an anomaly, you can compute it using local methods, using heat kernel methods you don't require. And from that you can get the Polyakov action for this field phi. And that action is given by so first of all, I will my space-time is Euclidean. I'm doing Euclidean gravity, but so d2x is signature is plus plus. I think there is some 4 pi. So this is called the Liouville action. And it's a very interesting conformal field theory. I mean, defined as a, shortly I will define it more abstractly using conformal bootstrap. But this action also has, the classical action also has some nice properties because it's a kind of a very special exponential potential. And there is a huge literature again going back decades about solutions of this and so on and so on and so on, which we don't really, I'm going to only summarize it.
What determines what mu is?
Mu is the cosmological constant, which is a parameter. It's a dimensionful parameter.
But can it be 0?
Yeah, so it can be anything apart from 0. So Liouville theory is defined for mu non-zero and mu positive actually.
Suppose we just did this path integral here. Will a mu necessarily be generated?
Okay, generically you expect that by there will be a non-zero mu. You can of course, in critical string theory one sets mu equal to 0 by hand.
Okay.
But we would be interested in, but the Liouville theory per se is actually kind of ill-defined for mu equal to 0. So it's, we will take, always take mu to be non-zero and positive.
At least in the old days, just for the 0 mode,
Yes.
you need
Yeah, just for the 0 mode. So when I give a more abstract definition of, yeah, so part of the motivation is to try to understand quantum gravity in the presence of the cosmological constant. So you don't want to set the cosmological constant to 0 to begin with.
Well, sorry, what did you say, Sanjay?
just for, like suppose you were trying to compute the sphere partition function or something. Just for the 0 mode, you need a non-zero mu. Otherwise, it's not well defined. You have to try and define it in some way.
Sorry, I'll just ask a remedial question. Like in Pulczynski's book, coming from the conformal anomaly, you see a c minus 26 or 26 minus c or something like that, r 1 by del squared r.
Where is that coming? Yeah. So I have, I have actually sort of did some normalization. I will write that in a moment. So the central charge of this is 1 plus 6q square. Okay. And this b is defined as q is equal to 1 upon b plus b. Can everybody see this? Yeah, okay. And then we impose in a gravity theory, so there is some matter in addition to this, there is some matter. So x is the matter. For example, it can be just some number of scalar fields which are free, and that with some central charge c matter. And that c matter plus c, this c, has to be equal to 26. Now, this 6q square is actually very easy to understand. 6q square is easy to understand because this is classical. Because under a while rescaling, when you rescale h, you also have to shift phi to keep g fixed. And under that, this action is, so this is kind of a classical piece. Classical piece in that the action is not transforms under while rescaling. And from that you can read out the central charge, that is 6q square. And there is a quantum piece which is 1, because roughly speaking the field is like a free scalar field. So there is a central charge of 1, the quantum central charge of quantum field.
Atish, I'll keep asking stupid questions, I'm sorry.
Yes.
Again, in Polchinski's book, you took the equation R is whatever, the T is equal to C times R, and you integrated that.
Yes, yes.
And I didn't see any cosmological constant in that solution. I didn't see any mu in that solution. You took the path integral. You derive an equation,
Yes.
which is that the trace of the stress tensor is central charge by 12 times R.
Yes.
And then from that you integrate to get, I think, what will give the first two terms here.
Yes.
You get R 1 by del squared R,
Yes.
which I think will be your first two terms. But where did that mu term come?
The mu term is always present, and classically it is invariant. You can always add to your integrated action term which is invariant.
It's like a counter term.
Yes.
It's more that if you had the critical theory, then you set it to 0 because
You have the option of setting it to 0, but generically it's always present.
Okay, fine. Well, it's like a cosmological constant?
It's exactly like cosmological constant. I mean, if your original theory had a square root of g,
So you can just add to it a square root.
d2x, times mu,
I see.
it will, square root of g
Okay,
will
now-
become,
now I see.
So actually I should say that this phi, I have done a bit of rescaling actually. So I mean, let me call this field phi tilde, no? And phi tilde is related to phi by rescaling. That's what probably bothering you. So, right?
Yeah, some C minus
B
26.
times phi, something like that. Phi tilde. If you just look at the classical cosmological constant, classical cosmological constant will look like square root of h times e to the 2 phi tilde, right? Just by substituting it directly, without regarding it as a quantum field. And if you just write phi tilde is equal to b times phi, that's the classical.
And then, sorry, Atish, just so that, I mean, there is a critical value of b across, either b is real or imaginary, right?
Yes, okay. So I will come to that
And
in a
that's
moment.
crucial.
Yeah, that's going to be very crucial. So now from this it's clear that if C matter is less than 25 or C matter greater than 25 is going to be different, because Q, if you look at this equation, then C is equal to 25, sorry, Q square, 6Q square is going to be 25. Because the 1 will cancel 1 minus C matter. So let me write it here. So depending on whether C matter is less than 25 or greater than 25, Q is either pure imaginary, is pure real or pure imaginary. And this corresponds to B being pure real or B being pure imaginary. And in fact, there is a kind of a window which kind of pathological. So what people have analyzed in great detail was C matter less than 1. And these are the famous matrix models of the 90s. And where basically everything is very well understood. People have computed correlation functions, they have done all kinds of checks. And there is a very nice story. But in some ways, that story is kind of uninteresting from the point of view of quantum gravity, because in that case, when Q is real, the sign of the kinetic term is positive, and it's a perfectly well-defined path integral. And it's not a big surprise that such a thing is well-defined. And it does not really give you a good model of 4-dimensional or higher dimensional quantum gravity. So if you are really interested in understanding higher dimensional quantum gravity, one must really try to make sense of the C matter greater than. Now, C matter equal to 25 is what is known as the critical string theory. With mu equal to 0. If you set mu equal to 0, then C matter is equal to 25. How does that come about? Because the critical string theory, as you know, has one time-like direction. So it has 25 real, so C matter is equal to 25. What about the time? And it turns out, I think this was an observation made by Schmidt and Spencer and so on, also by other people, but that the Liouville field itself can be viewed as the time direction. And hence the name Timelike Liouville. So this timelike and spacelike is really kind of a stringy, has a kind of a target space interpretation. If it's from that point of view, it's timelike or spacelike, because your world sheet is always Euclidean. There is nothing timelike or spacelike about it. What is timelike is that the target space is timelike. In the target space, the interpretation is timelike. How does that come about? See, if Q is pure imaginary, then it's good to make a Wick rotation, target space Wick rotation, or field space. Because as you know, if you think of this as a model of string theory, then target space is like the field space. And if you remember, Euclidean time is equal to I times Lorentzian time, normally when you do Wick rotation in field theory. So you just write phi is equal to I chi, and Q is equal to IQ. So now I am discussing this case. So since Q is pure imaginary, it's good to write it as Q is equal to IQ and make Q to be purely real, not pure imaginary. And then you take B is equal to minus I beta. With this redefinition, you get the Timelike Liouville theory. So this action small q r chi plus 4 pi mu e to the 2 beta chi. And because of this minus sign, it is called Timelike Liouville theory. And now the path integral is not, I mean, the action is real. The price you had to pay to get the real action was that the kinetic term is not no longer positive definite, and then the path integral is really not defined. Of course, in physics, you never shy away from path integral which is not well defined. What you are supposed to do is just choose an appropriate contour in the field space and try to make sense of that path integral. Right? That's the analytic continuation. I mean, the simplest example is if somebody give you a Gaussian integral, right? It's of course well defined when A is purely real and positive. But in physics or in mathematicians like Euler, they never shied away from trying to make sense of this. You just define, change the contour from this. And this is defined to be pi over A, which is a perfectly analytic function with a branch cut. And you can define this analytic continuation by rotating the contour of integration in the field space. So that's the general philosophy, that in physics, if you come across a path integral, the idea is to can we make sense of it by an appropriate analytic continuation of a well-defined quantity. And that's what one normally does. Wick rotation is exactly that's what one does, that you don't know how to make sense of Lorentzian quantum field theory path integral because there is an oscillatory factor. You just go to the Euclidean space, do the Wick rotation, and then all the results you analytically continue back. So you compute all the S matrix elements for Euclidean momenta, and then you analytically continue back to Lorentzian momenta. And if you can give an appropriate analytic prescription, then you can declare that those quantities to be well defined. So that's what one would like to do here. But the path integral is a fairly complicated thing. I mean, even for the space like Liouville, you have a very complicated exponential interaction. It's not even a 5-4 theory or 5-6 theory. All if you expand this, all terms are present. But at the same time, the exponential potential is very special. The coefficients are very special. And so it turns out, even for this space like Liouville, rather than trying to make sense of the path integral, the conformal bootstrap offers a much more powerful way of defining the. So let me now briefly review.
Sorry, Atish, you said something about C less than 1. Now, it was space like for C less than 25, right?
So
about C less than 1.
So it turns out that between the window from C less than 25, between 1 and 25, this B turns out to be imaginary, complex, yeah. So as a result, making sense of that window has been complicated, has been difficult. But I will now give a completely different definition. So let me see that. So this is the problems. Has everybody understand the problem?
The value of B is chosen to make the dimension of that operator.
Yes, 2. So that the whole thing is while invariant.
Yeah.
Sorry, just a small comment. Exactly at C matter equal to 25, that is Q equal to 0, there you can actually do your Wick rotation,
yes,
because the Q term disappears, and if you set mu to
if you set mu equal to 0,
then
but
you can,
yeah,
which is
but
what we do in
critical strength theory. But yeah, if you don't want to set, you could also be interested in the situation where you don't set mu equal to 0, and then you wouldn't know a priori how to make sense of it.
So can you state the problem also?
So the problem is that our original motivation to make sense of the Euclidean path integral of gravity, which has a negative sign kinetic term, exactly like Timelike Liouville theory. And Timelike Liouville theory arises very naturally in the definition of 2D quantum gravity. And it's an excellent model for a higher dimensional Euclidean gravity. And unlike in higher dimensional Euclidean gravity, we have much more powerful methods available to us in 2 dimensions. So can we make sense of this theory using those 2-dimensional methods? Right? So the idea is to learn something about Euclidean gravity, quantum gravity, in a regime where we can, in a model where we can analyze things.
So suppose you solve the space-like theory and then just analytically continue your answers in Q.
Yes.
That would be the wrong answer.
It turns out, so there is a very long and beautiful story which I will try to summarize in 10 minutes.
Okay.
Going back to Teschner and various people, Zamolodchikovs and DOZZ. It's a very beautiful subject actually, and with all kinds of, and so space like Liouville theory is a very nice example of, apart from minimal models, if you remember, minimal models were very interesting in early days because it sort of went back to this Polyakov's program that you just give a definition of a quantum field theory by bootstrap. There is no path integral, there is no action. You just state some axioms, and then completely abstractly you define that quantum field theory. Therefore, any mathematician would be satisfied with that definition. And minimal models in some ways are much simpler version. Liouville is another, the most non-trivial example of where the bootstrap program has been carried out to completion. So let me just remind you of that. What is the bootstrap? So what are the guiding principles, right? So first of all, the problem is clear, right? The problem is to make sense of Euclidean quantum gravity with a wrong sign kinetic term. And we are going to do that using conformal bootstrap, etc. So the first principle is, of course, that we have while invariance. This is kind of the fiducial while invariance because we sort of broke up the physical metric into fiducial metric times a conformal factor, and that breaking up is like a gauge invariance because you can always while rescale this and while rescale that, and so that's at some level it's a fake, but gauge invariance is always fake, so it's an additional gauge invariance that you have introduced, and we're going to use that as an additional principle, gauge principle, plus diffeomorphism, right? So we started with a theory which was diff invariant, but now we had also while invariant. And then one should do some Virasoro, it's a conformal field theory. One can impose Virasoro constraints and try to define exactly as one does in critical string theory, But a smarter way of doing it is to define some BRST cohomology, BRST quantization. And in the BRST quantization, one of the things that you would like to prove is to prove a no-ghost theorem. As one does in critical string theory, to prove a no-ghost theorem that the states in the BRST cohomology all have positive norm. Otherwise, your theory is not well defined. Your Hilbert space is not well defined. And if you, just to remind you, in critical string theory, the way one does that is that you show that the BRST cohomology is in one-to-one correspondence with the light cone quantization. And in light cone, everything is manifestly positive because there are no negative, there are no ghosts, there are no wrong sign kinetic terms. So if you just generate your Hilbert's Fock space using the light cone oscillators, the transverse oscillators, then everything is manifestly unitary. Everything is manifestly has positive norm. And if one can show, so the way the proof of no-ghost theorem goes, if you look back at Polchinski or the more BMP, this Buchnecht, McCarthy and Pilch, they had given a proof of BRST for C less than 1. That's what we will actually use. So you can prove you can try to prove a no-ghost theorem first. But more the non-trivial part, which sort of where we were kind of stuck for a while, for a long time, and where some French group made a very nice important progress, was that can you even define Timelike Liouville theory? So define using conformal bootstrap. And then the fifth step is that, what does it mean? What you want to show is that you have a 3-point function, a spectrum of operators is well defined, you have a 3-point function, and the 4-point function is crossing symmetric. If you can satisfy all these 3 conditions, then conformal bootstrap gives you a definition of that quantum field theory. And the point is that, but that actually will give you a definition of the quantum field theory for momenta. It's a bit like defining Euclidean path integral. See, if suppose you define a Euclidean path integral for say free scalar field, you still have to do an analytic continuation when the external momenta become Lorentzian. So just having the definition of the Euclidean path integral is not sufficient. So you need to do analytically continue external momenta. And here we run into another roadblock. So we had 2 roadblocks to try to really solve this problem. One was that the definition of Timelike Liouville theory was not clear, even using all the power of conformal bootstrap. And even if you could give a definition of it, it was not clear how to analytically continue the external momenta, because there are some divergences of the 3-point function which I'll come to. But a very similar problem was encountered in string field theory by Ashok and collaborators. And normally the one does analytic continuation by using Wick rotation. And I think the key point of the prescription that Ashok gave for and collaborators gave for the string field theory analytic continuation was kind of not do the Wick rotation, but sort of deform the contour analytically as you external. So give a kind of a smooth deformation of contour for internal momenta. So as you analytically continue external momenta, you need to also analytically continue the internal momenta. Normally Wick rotation just does that for you. In string field theory, you cannot do the naive string. This is string field theory at loop level. But a similar problem arises in Timelike Liouville theory at tree level already.
Internal momenta means d2x, right? Vis-a-vis the world, what we would have said, I mean, the space-time of 2D quantum gravity. Is that what you mean? I'm not sure.
Ha ha.
No.
Yeah.
I mean, what do you
Ha, by internal momenta, I mean so if you have some P1, P2, P3 like that.
Right.
P.
Oh, I see.
So it's really the target space momentum.
Okay. But for the intermediate.
For the intermediate states.
Okay, thank you.
Yeah, for the bootstrap, for constructing the 4-point function using bootstrap, you have to sum over the S channel, and that sum has to be analytically continuous. I mean, sum becomes an integral, and then you need to give a proper definition of that analytic continuity. So basically, by combining conformal bootstrap with a prescription similar to what one uses in string field theory, I think we have a consistent definition of. I mean, we propose it passes all the checks. So I think I'm sure that it's correct definition, and so it's a very nice model for studying interesting questions in.
So regarding point 4, is it clear, is it easy to see why this is equivalent to the usual changing contribution theory space?
Yeah, so that you can check. So the power of the conformal bootstrap is that it gives you a non-perturbative definition of the field theory. Whereas typically a path integral, you know how to define only perturbatively. So for space like Liouville, it is very well understood that B going to large, Q becoming very large is Q getting large is the semi-classical limit, and you can match the conformal bootstrap to the semi-classical limit. But clearly, when B is of order 1, the conformal bootstrap is much more powerful, and you get the definition of the theory. So, are there any other questions?
And then since you've given such a beautiful impressionistic summary, let me just ask you for one more, which is, so you show that your definition meets the consistency checks, but there's still the issue of then solving the equations of
Yes.
bootstrap.
And the amazing thing is that for both for space-like and time-like Liouville, there is a very beautiful explicit solution, completely explicit solution, thanks to heroic work by Teschner and many other people.
I see. For any value of little q.
For any value of little q, yeah.
Are you going to be imposing the constraints, the T mu nu equals 0 constraints?
That's the BRST quantization. Cube psi equal to 0.
So when you say you solve by bootstrap, this is before imposing the constraints?
Yeah, before imposing the constraints. So you basically, once you have conformal field theories, then you can impose the constraints, right? But or one can assume that there exists a conformal field theory, prove this, no-GOZZ theorem, and then show that actually the conformal field theory exists. I mean, you can do the different orders.
Atish, there is one question.
Yes.
The E, the momentum E that you described, right?
Yes.
What is that momentum?
I will come to that now. So why don't I first,
Okay. I just want to know if it's in X or in phi. Is it conjugate to X or phi?
It's conjugate to phi. It's related to related to Ashok's, Sandeep's question, that it's like momentum in target space string theory.
Okay.
Okay, so let me now erase this. So so now even if the link goes down, this is the summary that there is a definition of Timelike Liouville theory using conformal bootstrap, which is consistent in a very non-trivial way, and an explicit solution is known. This is earlier work very recent work by Ribault and Santachiara, building upon earlier work of Teschner. So we were for a while, we were discussing quite intensely with them and collaborating. But okay, their interest was mostly statistical mechanical. And then there was another step required is first to prove the BRST no-GOZZ theorem. This turns out to be relatively an easy step, and more or less, so again if the link goes down, if you have seen the proof of no-GOZZ theorem for critical string theory or for C matter less than 1 in the early matrix model days, thanks to Booknecht, McCarthy and Pilch, BMP, then that proof more or less goes through for the Timelike Liouville theory, essentially, without much changes. Because the Timelike Liouville theory, unlike the space-like Liouville theory, is non-unitary because of the minus sign. So all the standard things, the lore that you use in CFT or in Polchinski's book about unitarity, that doesn't work. And so you have to be careful, but the no-ghost theorem goes through. So that's one summary, one of our results. And the second result is that there is a way to define the analytic continuation of the Ribault-Santachiara definition of the Timelike Liouville theory, such that for all the external states in the BRST cohomology, the 4-point function is well defined and can be constructed from the 3-point function. So once you have done that, it's a definition of the theory. I mean,
and after you've imposed the constraints, the observables are integrated correlation functions, the kind of thing we do in string theory?
no, so that we are not going to do. I mean, that's a much harder. I mean, we don't have explicit answers for the integrated correlation, because as you know, to get the integrated correlation functions even for Virasoro amplitudes is yet another step from computing the correlation function.
But conceptually, we have to do the same thing as in string theory.
Conceptually, you have to do the same thing as in string theory.
Including course.
Yes, everything. So conceptually, the problem then is well stated, and it then further might require. I mean, you don't do loops and so on here. I mean, we are doing sphere partition function. I mean, we are thinking of it as a universe rather than as a multi-universe with handles and so on.
So, as far as a complete definition of 2D quantum gravity is concerned, this is complete.
Yes, I mean, I would say that this gives a formal, sufficiently explicit, but nevertheless formal definition of the, formal in the sense that it's not a path integral definition. It's an abstract conformal field theory definition, but with very explicit 3-point function, very explicit constructions of the 4-point function. But given that, you still have to further gauge fix and, do all this integration over the positions, because.
You see, this is not a definition of 2D quantum. Because in any quantum gravity theory, there are no local correlation functions.
Yes, so you're going to integrate D to Z. But the first step is that, first of all, can you compute the local correlation functions? And the answer is that you can. Secondly, are those local do you have a well-defined Hilbert space to start with? And the answer is you do, with some ghost number, with conformal. And then the next step is to do the moduli. I regard the problem of integrating over positions as the same as the integral for moduli space. So the moduli space integrals you have to do in any ways, always.
This is getting the integrand.
Integrand, but you have reduced then an infinite dimensional path integral problem to a finite dimensional problem, right? Here, that's to that extent you have solved the problem.
Once you have a conformal field theory,
Yes.
why can't you use the usual tricks for defining the integrals? What is the difficulty? You have a conformal field theory, right?
Okay, so I have to tell you what that conformal field theory is, but you're saying that suppose you know this Timelike Liouville conformal.
Yeah.
Yes.
And you know how to calculate the correlation functions.
Yes.
Then why should it be any different from normal string theory? Where you know, once you have the vertex operators of the conformal field theory,
Yes.
you know what you should integrate, right?
Yes. The trouble is that, like in ordinary string theory, suppose you do everything in Euclidean target space.
Okay.
And you compute the correlation functions for all Euclidean target space momenta.
Yeah, then of course you don't have on-cell
Yes.
condition at all, right?
Yeah.
You
And
don't have on-cell
yeah. So that is an additional puzzle that you have to. In string theory, that analytic intuition is fairly trivial for tree-level amplitudes.
But once you have the BRST cohomology, right?
Yes.
You have to control the momentum anyway, right? You probably cannot get non-trivial elements of the cohomology by remaining Euclidean.
Yes. So the thing is that the cohomology requires, I will come to that, states additional to the states that were used by Santachiara and this thing. So it's not a priori obvious. Yeah, so there is an additional step which I will come to in a moment.
Okay.
And I'm sorry, I'm going to another general question. Does this theory have a state operator map?
No, so this is a well-known thing that the state operator map is very subtle in very subtle.
So the BRST, this no-ghost theorem presumably is about states.
It's about states.
Whereas the things you will compute will have to do with operators.
No, so there are a set of operators to which there are no normalizable states. Like cosmological constant is a famous example. It's a local operator, but there are no normalizable state corresponding to it. And the way to think about it, yes, but you can always insert that in a correlation function. It doesn't stop you from doing it.
It will be one of the things you can insert in this.
Yes,
program.
yes. And so one should be able to make sense of such operators which are to which there are no normalizable states in order to define the theory, because for example you can insert cosmological constants n times, and that is one of the puzzles of trying to make sense of this theory. Okay. So let me, so the Liouville, I mean this Liouville, really giving a full thing of Liouville will take actually 5 or 6 lectures, because it's really a huge literature. And so again, I think, but I hope that I will convey the impressionistic thing clearly enough, and hopefully you can read our paper and then it will be all clear. Okay, the paper hasn't come out yet.
I'll just ask one more, sorry. This BRST, operationally for the observables that you will compute, what will unitarity mean?
What
Will
will?
it mean that there are space-time poles and that the coefficients of those poles are positive? See, what you will in the end compute using all this is these integrated correlation functions.
Yes, yes,
This is the thing that in string theory would be space-time isomatrices.
yes.
And unitarity there implies Kutkowski rules for those expressions.
Yeah, I don't know, I don't want to, at the moment I don't want to attribute such interpretation, because I'm thinking of it as a quantum gravity, but I think these are all very interesting questions. That first of all, yeah, you could also think of it as a supercritical string theory, but you cannot use some of the Kutkowski rule. I mean the whole thing doesn't go through here, because you have given up Lorentz invariance, because the time-like direction is not Lorentz invariant, it's not translational invariant. So it's not even clear what is the criteria for defining, I mean if you want to think of it as supercritical string theory, what would be the analog of Kutkowski rules? There must be some analog of that.
What are even the observables?
Yes.
Because in terms of supercritical, you have a dilaton which is growing or with
Yes.
time, let's say.
Yes.
So you have cosmology. You have to formulate what the observables are,
Yes.
right? Even
So
though
I
it's
think,
not clear to
yeah, and the thing is that all these very deep questions, it's good to have at least one well-defined concrete model. I mean that is one of our motivations. That now if you have a model where, okay, there will be issues like the dilaton blowing up, there is a tachyon, but I think one can try to then make sense of.
Sorry, the dilaton growing is not cut off by the wall?
Not in time like Liouville, because
Here it's not clear whether you have a wall.
but so therefore, yeah, this mini superspace analysis that was done for the zero mode, the mini superspace is just the analysis of the zero mode. And there it's very clear that you have a kind of a wall, it's a quantum mechanics problem, and there is a reflection that happens by the wall. And that's the essential content of the difference of the Liouville theory from a free field. That's why you need a. So let me now, yeah, but all that doesn't go through because the wall is like going down, things like that. So if you, the Hamiltonian is not bounded from below. It's not unitary. So, but surprisingly, an abstract definition exists. So I think this is what. Let me try to summarize that. So let's try to define a space like Liouville. Abstractly, okay? So, but just to set up the picture, this is the following.
Sorry, if you're not going to do the genus sum, then do you care if the dilaton blows up somewhere?
I was just saying, if you wanted space-time interpretation.
Okay.
Yeah, if you want the target space interpretation, yeah. If you're a 2D quantum gravity person, you don't care that the dilaton blows up.
Right.
Yes.
I was just thinking that formally integrated correlation functions are observable. So
Yeah.
what they mean is another thing.
Yeah. I mean, so those define, I give you the definition of all the observables. Now, how to interpret them, either you interpret them in target space, which is a completely different point of view. But if you're suppose just a 2D insect who wants to think of it as a quantum gravity, then these are correlation functions which are functions of some momenta and so on. I mean, some charges, some charges.
Yeah.
But then we have to think about what it means from the 2D point of view.
Yeah.
right?
Yeah.
I mean, so either way, there's a physics set
Yeah.
of questions.
So there is a physics question which one can try to address once we have explicit answers. So just to summarize it in a quick way, if you sort of look at the complex C plane, so suppose you complexify everything. So as I said, whenever you come across an integral like e to the ax square, right? This is an integral. So as a physicist or as a mathematician like Euler, you should always think of a as to be complex. Right? You have minus. And then you define a contour which depends on a in appropriate way. So you rotate the contour in the x plane as you rotate A. And that's how you define analytically continued formulas, right? So this you probably have seen in simple examples. I mean, this is an example where you can see it very explicitly. So we're going to complexify everything. Q is complex, B is complex. So C greater than, but there is something very special about, as Sandeep pointed out, C greater than, so this is 25 and this is 1. So because you remember it was C matter 25 minus, what am I doing? Yeah, C is equal to 1 plus 6 q square. No, C is equal to 1 plus 6 q square. So C becoming less than 1 corresponds to Q being pure imaginary. And C being greater than 25 corresponds to Q being. So it turns out that, okay, so using conformal bootstrap. Okay, so let me first actually define. So this is space-like and this is time-like. And what we will find is that there are two solutions to the bootstrap equations.
This is C of the Liouville theory.
This is the C of the Liouville theory. I'm always talking C of the Liouville theory. And C matter is Cm. So for space like Liouville, there is a 3-point function which is called the DOZZ formula of some. And here there is another a completely different solution which is called the DOZZ hat or C hat. So let me remind you what is meant by. So these C hat and C are very explicitly known in terms of Barnes double gamma function, which is some function, okay? It's like a Bessel function. It's a very explicit expression in terms of these Bessel functions, the gamma functions. All its poles and everything, the structure is a very beautiful structure, analytic structure, is all completely understood. But there exist two separate solutions of the bootstrap equation. And this solution fails for these values of C. Whereas this other solution fails for these values of C.
And sorry, Atish, DOZZ or whoever found these through the bootstrap method, is it? Or
So DOZZ did it with some very physicsy thing. They did some resonance, this. But then Teschner gave a completely abstract, and I think Ribault has a very nice review on that. Completely abstract definition. It's a very beautiful story. Completely abstract definition starting from the bootstrap axioms. In much the same way that the BZ, what is the? Yeah, BPZ, yeah, in exactly the same way that BPZ found the minimal models, Teschner defined Liouville theory. So I will let me now remind you very quickly about that. How much time do I have? I'm already out.
Till lunch.
Till 1:30. Director साहब का कैसे?
Never mind, I might have to go at one, but that's
The modular inline is required here also for implementing Liouville theory. Just like
No, I'm talking only at tree level now, so I'm not going to worry about modular inverse. I'm not doing one loop because I'm thinking of this two-dimensional world as a universe. And I'm not considering universes getting annihilated and things like that, right?
And you tell us what A1, A2 and A3 are.
Yes, I'm going to tell you in a moment.
so this C and C hat were both not discovered at the same time.
No, this was around 9, yeah, no, these were discovered earlier. And then after much work, Al Zamaldachikov gave this definition. Also there was a nice paper by Harlow, Maltz, Witten, trying to understand it from a path integral point of view. And basically, yeah, so let me summarize it. Sort of the most abstract definition, this was done by Teschner. So this is, of course, as it always happens, this is a summary of, I don't know, 50 people's work, very nice work. I'm just adding some label just for convenience. And this is Ribault and Santachiara. So So Santachiara was my colleague in Paris. He's a student of Dotsenko, so he's like the conformal field theory. And everywhere here, you can now do analytic continuation. But the C hat and C analytic continuation don't match here. So C hat is related to C by some function H, which is doubly periodic. Okay? So that's the reason you cannot just take this as what to answer your question. C hat is not an analytic continuation of C. They differ by some non-trivial function H, which is doubly periodic, which kind of blows up, which is not well defined here. And vice versa. 1 upon H is blows up here. So let me first summarize for you Teschner's definition of space-like Liouville theory, and then we can just jump on to.
So do either of these solutions continue to the range 1 to 25? Or both of them?
I was thinking both.
Yeah, they continue, but they disagree with each other. And there are all, yeah, there are.
There's no clear.
Yeah, I think some people, like there is Runkel-Watts theory, there are different theories which are people, from statistical point of view, both could be important. I mean, both could be useful depending on the context. So what is the, so let's just do the space-like Liouville bootstrap. So what is bootstrap? Bootstrap means you specify the operators and their weights and 3-point functions. Then a conformal field theory is completely well defined if it satisfies the bootstrap constraint, namely the 4-point function. So if you have some general 4-point function, you can sum it over as in the S channel. Or you could equivalently expand it in the T channel.
So you're looking at only the holomorphic half or the full CFT?
No, the full CFT. Full CFT. And these two things have to agree with each other. And that's an extremely non-trivial, non-linear constraint on the C's. And then sometimes, just by this constraint, there is a unique solution for C, given the spectrum. So therefore, Liouville theory I will define by the spectrum a unique, the spectrum covers an entire line. It's a continuous spectrum. So that is my definition of Liouville theory. Liouville theory is a theory where the spectrum of operators is over the entire line, moreover with unique multiplicity. Meaning there is a unique operator VA corresponding to a given weight HA.
So including negative weights.
No, it's a unitary theory.
So R greater than 0.
Yes. R whatever.
And what is the semi-classical representation of this operator?
Yes, I am coming to that. So let's just think of a free scalar field, right? A free scalar field is an example of a conformal field theory. And in the normalization that I will use, I will use the normalization e to the 2ikx. Suppose I have a free scalar field. So this is an operator Vk. Okay? But Vk, what is the weight of this? K square in my normalization. But notice that it's not a unique operator. there is a v minus k also, which is e to the minus 2ik, which also has weight k square. So a free scalar field satisfies the first condition, but it doesn't satisfy the second condition.
This is presumably a fact that bounces up.
And it's basically reflected because of the fact that the minus k and k. So there was a big confusion in the early thing, and there was a Seiberg had actually some wrong. I mean, people were confused by the statement that So let me just define. So therefore, you will define a v of a, which are going to be of the form e to the 2a. Semi-classical representation is this 2a phi. Let me call this p. Actually, it's better to call this p.
You're doing the space-like case.
Yeah, I'm doing the space-like case.
So there's no I. There's no.
Yeah, it turns out to be more convenient not to put an I. And the weight of this is a q minus a. So when q is 0, it's minus a square, consistent with the minus sign comes because there is no I. So q equal to 0 is free scalar.
But is a going to be a real number?
I will take a to be complex to begin with. And then, no, so the only condition that is required
Is that h is real?
H is real, yes.
H is positive.
So A is actually not going to be real.
Yeah. So it's like this q by 2 plus I in k.
Yes.
And then I guess there could have been two dressings. I mean, there could have been two values.
Two ways to take a square root, yes.
But one is not okay.
Yeah, one does not connect to the semi-classical limit. So
But q by 2 plus I k, what is the weight? Doesn't that have a minimum weight?
yes, it has.
So
So
then it's not exactly R plus.
no, it does have a. It is R plus. So in the A plane, if you demand that HA has to be real and positive, basically you can write it as this line is A is equal to q by 2 plus IP,
Yes.
but you also have this branch going from this is q by 2, going from to 0 to minus q plus q.
Oh, I see.
Okay, so A can take A is real is also allowed, whereas for if q goes to 0, you see A real is not allowed.
I see.
So P in this case, you see, in order to get positive H, P has to be real.
There are two different kinds of operators. Those
There are two different
those that don't.
yeah. And these are exactly these operators which are for which the state operator correspondence fails. I mean, this is the business with these are the operators for which there is no normalizable state. And these are the operators for which, even though those correspond to not to local operators. So there is a kind of you have to choose what you want. But the way to make sense of it, I think, is kind of something that we know, and this was Tishner's point of view, and I think I subscribe to that point of view too. That I mean, the way to think about it is that then what do you mean that if these operators do not correspond to a state, how do we think about it? It's a bit like how in quantum mechanics the x and p do not belong to your Hilbert space, right? The state x and state p, because they are not normalizable, the delta function or but you can nevertheless talk about them in correlation functions. There is some kind of this notion of Gelfand. If you take a sufficiently smooth, even though the norm of these states diverges, its overlap with sufficiently peaked state is well defined. And there is a more formal definition called the Gelfand triplet. So that is the way to think about it, that if you computed the correlation function, 2-point correlation function of these operators, it will diverge. But if you compute a correlation function of this with sufficient number of well-defined other operators, then it is a well-defined. So you have to therefore broaden your, like in quantum mechanics, you need to broaden. If you want to talk about x and p, you need to broaden your notion of the Hilbert space.
So if you take the OP of two of those oscillating guys, will one of the non-oscillating guys be produced?
No. Well, okay. I think it can be produced. Let me think. Depending on p, if the p can cancel. No, sorry. So a priori it is possible. There are some, because there is no conservation of momenta.
So if it was not produced, then one could restrict us.
That's what I mean. Yeah. No. No, but moreover, you do want, after all, cosmological constant is a very typical operator. And if you cannot make sense of that operator, then you are haven't defined the theory. So you cannot not talk about this operator.
Okay. I was just wondering whether there was a sub-solution inside your big solution of just the normalizing case.
Maybe there is actually. Okay, maybe there is. And maybe that's, okay, so let me continue for now. So is this clear, the definition?
How is the multiplicity?
If you take OP of Q by 2 plus IP with Q by 2 plus IP prime, so P and P prime don't add, that is true. But Q's don't add also. Q by 2 and Q by 2. The P gets reversed, right? Your P runs over positive values only.
Yes.
So take the product of these two. Q by 2 plus
Yeah, I mean, another way to say that this is a question about the 3-point function, right? So let me write down the 3-point, I mean, by looking at the 3-point function, we can figure out. Right, given A1, A2 to be this, does A3 have to be this? And I cannot answer that right away because it's a complicated 3-point function, but the answer is known. I mean,
it will be a continuous function of A.
It's a continuous function, so there is no.
Even though in the momentum it looks like that two different kinds of operators.
Yeah, exactly. So it's a continuous. Yeah. Yeah, it's a function of A1, A2, A3. It's a analytic function. So there is no natural selection sector like A1 plus A2 has to be this or something like that. There is no natural selection rule in general.
I see.
Okay, so let me now summarize.
So these things are non-normalizable because they're peaked in the direction of the wall. Is this right?
Yeah, so that was the understanding of various people like Polchinski and Seiberg had various, that the wave function, if you do some mini superspace analysis, so there is a wall like that. And if there is a local operator, it has to be peaked around here because the metric is actually e to the involves, and because of that is non-normalizable. So local operators correspond to non-normalizable states, and normalizable states correspond to non-local operators. So there was some slogan like that.
I see. But just algebraically, this guy is non-normalizable in that on the right or on the left? Where does it blow up?
It's here. Non-normalizable, it is here. Yes.
It blows up that.
Yes. Yeah, because here it is exponentially damped, right, because of the wall. Okay, so how did Teschner find this? So what he did was that he looked at what are known as now Teschner relations. And I'll just give you again a brief summary of one-line summary of Teschner relation. See, so this is a very complicated nonlinear equation involving 3-point functions and the conformal blocks, right? Because it's a quadratic equation. What Teschner said is that if I take A1 to be one of the degenerate fields or A4 to be one of the degenerate fields, then I get much simpler and finite set of equations. So what he means by is the following. So the degenerate fields, so e to the 2a phi are my fields, okay? And ARS is equal to S minus 1 or 1 minus R, I forget. 1 minus R, I think there's some minus sign issue. If you remember, this is actually also something that might remind you of the minimal models. Since you have the RS, that RS integers these are the degenerate fields. So for these values of A, you have spurious states and things like that. This business of degenerate states comes in. But you don't need to remember all that. I mean, so if you take in particular 2, 1 and 1, 2 operators. In this case, ARS is going to be minus B over 2, and or ARS is equal to minus, let me call it A4. So if I choose A4 to be one of these special values of A, then what happens is that this state is satisfies the Virasoro constraint, but it's also, it's a degenerate field, so you manage to get differential equations. You see, I don't know if I don't want to now go into that, remind you of the CFT, but the end result is that there is something very special about these states, because of which the bootstrap equations can be simplified enormously. And the net result is that you basically get simple linear equations. So you get a simple relation C A1, because you can sort of see it's like a shift by B. So you get A1 plus B A2 A3 is some function times the same.
Sorry, what is this realism that you say?
Okay. So in our definition of abstract definition of a conformal field theory should have C which satisfies this. The way of gluing this is determined by the conformal blocks, which is kind of universal, which doesn't depend on the theory. So roughly speaking, the way to think about it is that, like in a quantum field theory, right? If you know the spectrum of particles and the 3-point interactions between them, then you can construct any higher point amplitude, right? Assuming that you have only 3-point interactions. That's the similar statement. Its conformal bootstrap is a similar statement. But then you have to make sure that the result thing that you construct, there are two different ways of constructing your 4-point function, and those two different ways should agree, right? If you demand that, that's the bootstrap constraint. Okay, this is the conformal bootstrap constraint, and that in general is very hard to solve. It's a quadratic equation and it's impossible to solve. What Teschner realizes that if you choose one of the A4s to be the degenerate field, then the conformal bootstrap becomes a very simple linear. This implies this.
And it implies it for A1, A2, A3 being anything, presumably.
Yes. Where f and f tilde are explicitly known functions in terms of some gamma functions. And using this, you can solve for C completely. Now, it might look amazing that you can solve for C completely, but it's not so, because ZB is dense. Meaning if you know, suppose I want to calculate A1 for an arbitrary A1, I can write arbitrary A1 as some m times B plus some n times 1 upon B, always. I mean, you can approximate it as closely as possible. And then using analyticity, so it's not surprising that such a thing exists. But this is true if is dense, if B belongs to R or B belongs to IR. Right? Because why? Because in that case, B and 1 upon B are in the same direction. So suppose this is B, this is 1 upon B. But in general, for a complex B, B and 1 upon B are not. So what this gives you is a doubly periodic function. Meaning, any solution will be ambiguous up to a doubly periodic function because it's not uniquely determined. And that is the source of this non-uniqueness. So that's why you have C and C hat as separate solutions.
Sorry, what does doubly periodic mean? Once just sorry.
Doubly periodic means, now you think of this as a lattice. Okay, so suppose I find one solution of this. I can always multiply it by some doubly periodic function and it will still satisfy the same equations. And that's why C hat and C are related by a doubly periodic function.
Periodic with respect
To B and yeah. So if you think of B and 1 upon B as a lattice, when B is real or pure imaginary, the lattice sort of collapses. And then B and 1 upon B give you two things using which you can approximate any real value of A1 as close as you want. It becomes dense. So that's the key to Teschner's solution. And using that, he solved it. I mean, of course, using earlier work of Zamoldajik of DOZZ. So the formula is known as DOZZ formula, not Teschner, because they discovered it by various methods, by using Russian magic. So that's the summary of Timelike Liouville, and in fact, this is the summary of both Timelike Liouville and Spacelike Liouville, because the same solution works. So it turns out that for these two cases, you get C and you get C hat.
And the spectrum in Timelike Liouville theory once again has the same character?
Has the same character, but now we are relaxing the unitarity. It is real, H is a real. But
Real allowed to go arbitrarily negative.
Yes.
So, so the spectrum is labeled by H from minus infinity.
Yes. So, in the Timelike Liouville case, the operators are 2 alpha chi by this analytic continuation I had done. If you remember, phi was I chi and A is equal to minus I alpha, if I do write like that. And B was equal to minus I beta, Q was equal to IQ. Okay, if you just do this substitution, you can see that C becomes 1 plus 6q square becomes 1 minus 6q square. And therefore, it can be arbitrarily negative. And Q is equal to 1 upon beta minus beta.
And your operators are e to the power 2 alpha chi, but
Chi.
alpha real?
Alpha not real, alpha not necessarily real, again like in the case of A.
Yeah.
But H A real. So, H A now, which if you remember was Q minus A, becomes alpha Q plus alpha. So, if you write alpha is equal to minus Q by 2 plus IE, now I will call this energy, just to remind you that this is like energy in. Then HA, again there is a line like this, E real or this. There are two possibilities for which HA is real.
One possibility is alpha just real, right?
One possibility is that E is equal to 0 and alpha actually just spans this.
Real.
Yeah, right.
And the
Other possibility is that E is real with this because the same way it happened.
Fine. Fine. And the alpha real has a minimum value of something.
Q square upon 2, things like that. Yeah, Q square upon 4.
Four.
Yeah, Q square.
And these guys fill up the others.
Yes, exactly. So therefore, both spacelike and timelike Liouville explicit solutions have been known. I won't write down these solutions, but they are known in terms of Barnes double gamma functions. But the main idea of the Barnes double gamma function is that just like the gamma function.
So what is E and minus A gives the same dimension, right? So you just count only half.
So that was the confusion. So let me. There was a confusion in the early analysis. For example, in Seiberg's work, there is confusion about. So Seiberg concluded that the operators so he concluded that operators with Q minus A do not exist in this theory. But the modern interpretation is that basically given an operator V of A, it's related by reflection to Q minus A. So it's not that the operators don't exist. You just take one representative. There is a doubling of operators.
Okay.
So there is the modern interpretation is slightly different from what the early people were confused about.
So there's reflection even of the timelike wall.
No, so in the timelike wall you do in the timelike wall there is no such simple interpretation in terms of reflection, but there is a similar phenomena of halving of the spectrum. I mean, because you are defining your timelike Liouville by this criteria, that there is a unique state correspondent. There could be more general theories where that is relaxed. I mean, a priori there is no reason in timelike Liouville.
Right.
There is no semi-classical reason why that should be the case.
Just to understand, I mean, does that mean when you look at the bootstrap and so on, you make a choice and choose one of the two representations and it works, or it would work if you allow external states for both?
Yeah, so there is a huge amount of, there is a lot of evidence, first of all by mini superspace calculation, simply that basically it's like a e to the I p dot x. If you send in, it comes back with some reflection rp e to the minus I p dot x, right? So what actually happens is that the correct state is a linear combination of this with a particular reflection coefficient. And that reflection coefficient people have computed using both mini superspace, like this kind of a zero mode analysis, or more abstractly using Teschner. There is a computation and they agree in certain ways. So, so therefore, it's basically no more exotic than if you had a wall, then e to the I p dot x and e to the minus I p dot x. You don't say that e to the minus p dot x doesn't exist in the theory. You just say that there is only one operator corresponding to the e to the I p dot x plus reflection times e to the minus I p dot x.
Right. Okay, I understand that, but just in terms of how the bootstrap is supposed to work, is it supposed to work for all external states corresponding to whether you choose V of A or V of Q minus A, or do you have to make a choice and then it works? I mean, just to understand how.
Yeah, basically the point is that the V of A, I mean, even though I wrote V of A like that, is actually this is just a semi-classical representation, right? The correct way to think about it is that V of A is an abstract operator, which actually is a linear combination of this plus something else.
Okay.
He's labeling the operator just by H.
Yeah.
There's a unique operator for it.
Yeah.
Okay. And then the bootstrap just gives you a C, etc.
Yes.
That's what you do. Okay, thank you.
But even the data for the time-like and the space-like are different, right? Because one goes over all of R.
Yes.
And one. So it could.
It's a unitary.
Different at a very, in a very fundamental way.
Yeah, it,
Spectrum of operators.
but it is real. I mean, it's also similar in a fundamental way that it is real, and but it is we understand why it is different because it's not a unitary theory. So there is no reason for it to be positive.
Right.
What goes over R?
No, he's saying that the weight in a non-unitary theory doesn't have to be positive. Right? But we are used to that in even in critical string theory, right? That you have minus e square. The weight is minus e square, and we get minus e square. We have to allow negative energy. I mean, negative weights. Otherwise, we cannot get solutions to the. Yeah. So there is no on-shell cohomology.
Right.
BRST
I was just saying that there's no, a very elementary sense in which one solution doesn't continue to the other, because just the data is different.
I mean, analytic continuation doesn't work.
Yeah.
Yes. Okay. Any questions? So okay. So let me now try to summarize the remaining part. So let me summarize first of all what we have so far, right? So we wanted to define Timelike Liouville theory and quantum gravity. What I have shown you is that, we wanted to define quantum gravity with a negative kinetic term, negative sign, wrong sign kinetic term, and for that we needed to define Timelike Liouville theory. But for that Timelike Liouville theory, Teschner, we could use conformal bootstrap, and Teschner has found, Teschner and various people in that community, there are two solutions which exist, C and C hat. But what was not clear for a very long time for the C hat theory was that, so Teschner relations are in some sense the degenerate crossing relations. But that is not a proof of Liouville theory, because to prove the Liouville theory, you see, Teschner relations followed from taking a very special external state, namely the degenerate field. But you should show, in order to prove that the theory exists, you have to show that it is true for all. And in fact, it could very well be that some of these solutions are not solutions of the full non-degenerate.
Sorry, just repeat that point.
Yeah. So Teschner relations, the Teschner C and C hat were obtained by solving the Teschner equations, which in turn were derived by using the degenerate crossing symmetry equations, meaning one of the fields was a degenerate field. So it was a very special external state, and therefore A1, A2, A3 were not taking all possible values in some, I mean, in that 4-point function, right? You were taking, so you were taking C.
A1, A2, A3 could be anything.
Could be anything, but A1, A2, A3 could be anything, but you had sort of checked the crossing symmetry equations only for a special sets of A4. Yeah, A1, A2, A3 could be anything, but A4 had to be something special. So it could be that once you vary A4, you no longer satisfy the crossing symmetry equation. So we need to actually and choice of the contour. So this was done by this RS people. They basically, so the RS, they have two new results, which the paper that appeared last year or a year before. One result is that they have a numerical check of non-degenerate crossing symmetry.
I see. So namely, it works for all even. You take your 3-point function and crossing works for all even.
Yeah, for space-like Liouville. So in some sense, they really proved, at least numerically, that space-like Liouville theory exists as a quantum field theory. It's an extremely powerful and non-trivial result, right? It's a highly interacting quantum field theory, two-dimensional, nevertheless. You don't even postulate anything about its action. You just impose bootstrap, and you say that there is a unique state, unique operator for a continuum of spectrum, and there is a unique solution. For space-like Liouville, there is a unique solution, C, and it satisfies the bootstrap constraints. So it's a very beautiful result.
Okay. So Atish, here the bootstrap constraint will involve the integral over the intermediate state on both channels, right?
Correct.
And the C's are given.
Yes.
So it's a question of checking equality of two integrals, is that right?
Exactly. And you have to now know what intermediate states you're going to allow.
That's not running over all the real line?
It runs over the real line of P. It runs over only the normalizable. So you remember, the integral is because
even though the C's are non-zero, you are saying that you don't include them in the intermediate channel.
yes, the intermediate channel, because intermediate channel requires you to insert a complete set of states, right? So you need a normalizability, a notion of normalizability to insert a complete set of states. So this was kind of understood already in old days for space-like Liouville, that the states that you sum over are just for P, only for P real, and you don't sum over P imaginary.
Okay.
Then RS gave this second new result that they have is that they give a definition of Timelike Liouville. Yeah, so here when you do a numerical check, you do a numerical check for P real.
Sorry, could I ask about? Suppose I put two operators inside a disk. Now, if those operators
On a sphere, let's say.
No, I'm trying to work through your argument that you sum only over these normalizable guys. So suppose I put two operators and surround them by a disk inside a disk. Now, if those operators were going to create a normalizable state, then clearly you have to sum over these guys. But I thought you were going to allow the insertions of things that were not going to create normalizable states. So it's not clear to me that this whole, I'm sorry, it's a stupid question. But
No, it's not a stupid question. The point is that what you require is that, see, for example, if you take a delta function state, right? It's exactly like.
I see. You see, even it has a basis.
Yeah, the point is that suppose you're computing xy, right? Xy I can always write as xn ny sum over n, right? So this is psi n star, psi n x, psi n star y, where psi n and psi r are completely normalizable.
I see. So you're saying
You don't insert here x, it doesn't make sense to insert x here, right? Because
so even though the state is not in your Hilbert space, you will have a representation of it in terms of states in the Hilbert space.
yes.
So this would work for delta function, but it wouldn't work for e to the power ax, for instance,
But
right?
so there the notion of it's some kind of a notion of Gelfand triplet at the level of operators, which is not.
So the states are not too badly non-normalized.
Yeah, exactly. That's the idea. Exactly right. In the same, so there is a notion. So let me remind you, like in quantum mechanics, right? How do you? There are all these theorems, right? That what is it called? Some Hellinger theorem. That in quantum mechanics, if you have an operator whose domain is the entire Hilbert space, then the spectrum is necessarily bounded. Okay, there is a theorem of somebody's theorem. And every operator that you encounter, Hamiltonian doesn't have a bounded spectrum, right? X and P do not have a bounded spectrum. They don't have that. So how do we make sense of it? The way we make sense of it is that suppose you take a Hamiltonian, right? The Hamiltonian acting on a normalizable state. Suppose the Hamiltonian harmonic oscillator, right, has a term like x square. So x square acting on psi of x need not be normalizable, right? Even though psi x is normalizable, the Hamiltonian will take it outside of the space of normalizable. So the space on which the Hamiltonian acts has to be very, very nicely tempered, very nicely falling off functions. I mean, Hermite polynomials, as you know, is exponentially falling off, right? So that multiplying it by any number of times by x square doesn't make them non-normalizable, right? So it's the domain of Hamiltonian is a sub thing of. Okay. Now, if you go to other operators like x and p, which are not even defined in the physical sense, in the mathematical sense, but Dirac used it all over the place. People gave a meaning to it by, I think, Gelfand and company, that given a Hilbert space, there is you think of nice test functions. I mean, this is how you do physically, right? Use very smooth, exponentially falling off test functions, which is a subspace in the space of normalizable functions. And the operators are defined on the dual of this space, which is called S prime. So that's called the Gelfand triplet. So even though the operators require a bigger space than the Hilbert space, and that is obvious because e to the I p dot x is not normalizable. Delta function is not normalizable. But you can make sense of it, and even though those functions do not belong in H, they have finite overlap with all states that belong to H, right? And that's all that is required. So to make sense of the Liouville theory, you require some kind of a generalization of this notion for correlation functions of operators. And okay, I don't know whether anybody has really done a systematic job of it, but okay. But that was Teschner's basic idea, and I think philosophically that's correct. Okay, so I should really wrap up now. So where were we? So they gave a definition of Timelike Liouville, and then in that, if I don't change the notation, meaning if I don't do this, then I think in that case P has to be pure imaginary. Meaning,
P is defined as
yeah, so the point is that the 4-point function so a 4-point function I want to define, right? I have some 4-point function and inserted at, and I have not done the integral yet over the moduli. So I want to get a 4-point function by summing over DAS so this turns out to be the times some conformal block, S channel conformal block. So the 4-point function has this kind of a form, and the prescription of Ribault and Santachiara was that you do this integral along a particular contour in the p plane, meaning along the real p axis.
Why Q minus AS and AS?
Because of some, you have to take some BPZ conjugators.
They have the same weight?
They have the same weight. As I told you, those are the reflections.
Abstractly, it's just the same.
It's the same thing. Okay.
So what is this? So the 4-point, the C4 is the 4-point function, is obtained in this way through B.
Yeah, so there can be an intermediate state of AS, but you have to do some BPZ conjugations. Because of that, I think there is
And then fold it with this F, which has got
some information about but it's purely conformal field theory, group theoretic information. But now the point is that okay, and they checked that numerically it satisfies the bootstrap. So I think this is the solution, and it turns out that the contour that they have to choose, I mean, because of these degenerate fields for values of p, there are actually poles along the contour. So they have to shift the contour slightly above the real axis, and they show that whether you do it below or above, it doesn't make a difference. So
and the measure is DAS. That comes from norm in Hilbert space.
Okay. This I'm not 100% sure, but I think it is. It's probably dp. Yeah, but I think it's the same. It's linear in p.
So the way you have written, it's along the imaginary axis, right? So you mean on the left or the right of the imaginary axis? Is that what you mean?
Yeah. So in fact, sorry, maybe this is p in imaginary.
Yes.
Sorry, I should probably write ps maybe.
How are you labeling your exponent q plus ip?
Yes, q plus ip.
Q by 2 plus.
And then
Q by t plus ip.
q by 2 plus ip. And then you are saying p is imaginary. No, p should be then real.
No, but the thing is that, but then, okay, so there are two ways to do it, right? I can write as 2a phi,
Yeah.
and then I can continue phi to be chi. I mean, I can write phi is equal to I chi.
Okay.
And then instead of momentum, I can talk about energy
I see.
and keep energy real, or talk about momentum and keep momentum pure imaginary.
Okay.
Okay, that's one way to think about it.
I mean, in some notion where P was real for space-like,
Huh.
it would be imaginary.
Yeah,
for-
that's the main point. That in some notion where, some normalization where P was real for the space-like Liouville, it's imaginary here.
Actually, now we're talking about time lag.
Yeah, we're talking about Timelike Liouville.
Okay.
Yeah, because it's C hat.
Ah.
But now, if you look at the cohomology, you see, so first of all, then we proved a no-ghost theorem, and I won't tell you the details. I mean, it's more or less follows.
Even in the time lag case, you sum only over the q by 2 plus ip?
Yes, yes.
I see.
And the point is that the on-shell condition, if you remember,
That's
is
why
going.
I was sort of asking you, I mean, at least in terms of the wall and all, that's much less clear. Right?
Yeah, it's much less clear. It's much less clear. So, so Timelike Liouville is much more abstractly defined. It's really abstractly defined. There is no, as far as I can see. We did some mini superspace analysis, but we were, I mean, we were not getting, you know, like in space-like Liouville, people who did mini superspace analysis could more or less reproduce the reflection coefficients correctly. Here, the mini superspace analysis does not give the on the nose reflection coefficients. It's some
What
funny.
it suggests we should, of course, leave
Yes.
this for discussion very much is a target space interpretation where the initial wave function of the universe,
Yes.
initial conditions have to be rather specific.
Yes.
Quantum gravity.
Uh,
This is the most interesting thing.
I totally agree with you. I mean, that's sort of one of my motivation is that how does one, yeah, I mean, this issue of the initial state of the universe is a very subtle question, and nobody really has anything, any concrete. You know, you just do a Bunch Davis as your starting point, but there is really no reason for Bunch Davis. I mean, okay, maybe in after some inflation, absolutely the real, or near the singularity, it doesn't have to be Bunch Davis. Yeah, so all these very interesting questions, presumably one can answer. But now the point is that, let me just very briefly summarize. The point is that, see, if you remember, the on-shell condition is something like m square, which is equal to, okay, let me write, minus, okay. See, m square was equal to, if you remember critical string theory, it's e square minus p square, and it is some n minus 1, right, for bosonic string, where n is number of oscillators minus 1. The minus 1 is coming from the 0 point energy, right? And so n is equal to 0 is the tachyon. All that happens is that E gets replaced by HE. And HE is something like minus q square upon 4 minus E square, sorry, plus E square. So there are a huge number of solutions to the BRST cohomology in which, so E being real is the same as P being imaginary. Sorry, this I should call this key, sorry. So I'm using P for the momentum of the space-like thing, E for the momentum of the time-like Liouville, and K for the momentum of the rest of the fields, you know, X. So you see, there are lots of solutions where, and like cosmology, so the main point is that your required external states which are not the same as the internal states over which you're integrating. I mean, for this, I mean, you're required to deal with operators which are exactly the operators for which there are no normalizable states in your external correlation functions. Like cosmological constant itself is an example, right? It certainly is a right, cosmological constant, right? If you think of it as a tachyon vertex operator, it's not e to the I Ex, right? It is with an imaginary E. So you require both real and imaginary E to make sense of your theory. And then the question is that can we take this RS prescription and analytically continue the external momenta to be whatever are required by the BRST cohomology and still be sensible? And in general, it's not possible. I mean, as was I mean in string field theory, and so one of the main points where sort of the analogy with string field theory is useful is the following. So normally in quantum field theory we do sort of a weak rotation, right? You compute everything for imaginary energy, but you are really interested in computing things at the real energy with poles which have some structure like that. And as long as you can rotate, like that. And the weak rotation is guaranteed that it avoids any poles, and moreover the contribution from this part is 0 because they have a nice fall off. One of the things that was encountered in the context of string field theory was that because string theory has a very soft behavior, UV behavior, for space-like momenta, the vertices of string field theory have terms like e to the minus plus e square, okay? So when e is Euclidean, they are nicely damped off. I mean, for space-like momenta, it's nicely damped off. But since this factor blows up on this, you cannot use the usual weak rotation because you cannot argue that this contribution is 0. So therefore, how to define this was a problem. And so this was the famous I epsilon prescription problem. So Witten had some work on that, and Ashok had a different perspective from string field theory. So the main point, main observation of Ashok and collaborators was that there is no, the main thing to define analytic continuation is not that you have to be able to weak rotate at infinity. As long, what happens is that suppose you even compute, say, a 2-point function, a 4-point function in quantum field theory, right? Suppose you computed a 4-point function like that for lambda 5 for theory, right? It will have some poles. So suppose this is external momenta, K, P, let's say, and this is internal momenta, L. Okay, let me call it K, not to confuse with P. Then you have some, initially your contour is going over the imaginary L. L is the energy and K is the energy also. And you have some structure of poles which are like this, you know. And you want to now analytically continue the external momenta to be Lorentzian. Then what happens? These poles are functions of that external momenta because you have terms like L square plus m square, which doesn't depend on the momenta, but you also have terms like L plus k square plus m square, right? Right here it is L plus k. So this depends on the external momenta. So the poles start to move. So for example, this pole can move like that. But as long as you deform the contour, so if the pole moves, you just declare that I'm going to deform the contour to avoid. It turns out that actually, so in Liouville theory also there is a similar phenomena, but in fact it's actually simpler than in string field theory, it turns out in the end. So we were sort of inspired by this analogy. I mean, actually Harold, who wrote this nice review with Ashok on string field theory, a nice paper with Ashok on string field theory, and then he wrote a review. So he made this observation that yeah, so the trouble in the analytic continuation is that the 4-point function as a function of external momenta goes as, okay, or the 4-point function basically, the main point is that it has some behavior. As a result, the 4-point function goes as some positive quantity q to the power, I mean absolute value q to the power 2 times p internal ps square. So whenever ps square is negative, so ps, and we are interested in ps going to infinity, limit, or maybe with a minus sign, I don't know. The main point is that for ps real, this converges nicely, but where ps purely imaginary, it doesn't converge. So you are sort of encountering the same problem that you cannot do the standard weak rotation that you normally do. But it turns out that but one could use exactly the same kind of idea that one used in string field theory, that you just analytic continuation only requires that you smoothly deform the contour without encountering any poles. And if you are allowed to do that, then it turns out that in fact things are a bit simpler in Liouville theory, that even though it has this divergent behavior, the poles actually don't move. The poles, turns out, they are located at some zeros of this Barnes double gamma function. Sorry, poles are located given by this. So they are located at where this function goes to 0. And those clearly depend only on the internal momenta. They don't depend on the external momenta. So it's a bit like a pole coming from L square plus M square, not like this. So since the poles don't move, you are allowed to do the analytic continuation. And therefore, this gives you, and one can numerically check this, that you can take the external states to be in your BRST cohomology and use the program that Ribault-Santachiara have, and you will get a finite answer for the 4-point function, and which is guaranteed to be crossing symmetric, because you can check that it's crossing symmetric.
So the internal contour doesn't change at all. Is that what you're saying?
Basically, you don't change the internal contour, and so the main so the final simple observation is that analytically continuous external momenta does not require you to change the internal contour. So one can just use the Ribault-Santachiara contour and take the external states to be whatever are required by BRST cohomology. It gives you a well-defined 4-point function with the C hat definition, the Timelike Liouville DOZZ formula. So I think I'll stop here.
Just to ask you one question, just in terms of fitting, and then we can say later, there's also some story of brains, right, in the space like that.
So there is a DOZZ brain, and so for example, I originally started with saying the motivation is ADS, but see, ADS has a boundary. So that requires you to deal with, this was all on sphere. So if you want to do a disk, then that's like doing D brains in, and there some results are known. I mean, so I think a nice generalization of this would be to do the thing on the disk. I mean, that's clearly an interesting problem to look into.
And then just to come back to if we think of
Cosmological interpretation.
if we think of it in terms of target space.
Target space.
So I think you can adjust the sign now. I mean, either there's dilettants getting very weakly coupled in the far future or very strongly coupled, right? But if we invert it, so it was very strongly coupled in the far past, let's say.
Yeah, that's what one would like to do.
That's what you would like to do.
Yeah.
Then it
So that
seems-
you don't know what the initial state of the universe is. It's a bit like
Right,
you are in the strongly coupled gravity region
right.
in the early past.
And then, okay, we neglect loops and all that.
Yes.
But just look at what we are getting in terms of the conditions on the states.
Yes.
There's some interesting conditions.
Yeah, I think there is, so I mean, these are interesting questions. I mean, I have not started to really think about them, I mean, formulate them very clearly, but okay. I think they, presumably, one can ask interesting questions from this model.
But it seems like you have some analog of particle production, right? Because you don't just have e to the IET or e to the minus IET, but some combination of the two.
I see.
Roughly.
Good point.
So it seems like your initial singularity creates particles. And then it will be interesting to see if
to
there's
see
some
what happens.
physics story
Physics
there.
of that, yeah.
But what would the vertex operator be? I mean, so there's some, let's say some cosmological state, and that can be perturbed by the vertex operator?
I'm not sure myself, but
But you see that, suppose you have some matter, X,
yeah.
then can you generate matter, right?
Yeah, that's what I was thinking.
Suppose you have a two-dimensional scalar field, starting in a vacuum, can you generate particles for that corresponding to that state?
I'm not sure what the observable is, I agree, but I was just wondering, at zeroth order, there seems to be some space-time picture. You have very strongly coupled initial conditions, and some dilettone which is linearly varying. And the kind of physics question this would prompt is, okay, okay, at late enough time, you know, what is the particle production you've got, or the
Yeah,
spectrum of
things like that. Or do you land in a continuous vacuum?
Yeah, something like that. Right, right. Now, exactly to convert it into a well-defined, I don't know.
Yeah, but even this zeroth order question is interesting, meaning, yeah, we have always, okay, in matrix model it was clear, I mean, you always had integrated operators, I mean, what you got. Yeah, but here I think there is a semi-classical model, I mean, something which relates to a semi-classical theory, and one can ask what are the observables and what do they signify?
Right.
Yeah, maybe it's like the like inflationary correlators.
Yeah, that's what I was thinking. In the zeroth order, you can ask about particle production in the time-dependent field. Then you want to be more subtle.
Yeah, your observables are for each vertex operator. There's an integrated correlation functions. Suppose I put m vertex operators, and I integrate them over the world sheet. Maybe that will tell you at late times what the inflationary fluctuations of these things.
But the inflationary fluctuations are normally not integrated vertex operators, right?
In space-time,
In your space, right?
well, you know, I mean, here we are thinking of it as target. Okay, there are two things. Let's say we are not doing 2D quantum gravity, but thinking of it in target space.
Okay. You were interested in some kind of a district for that? You were interested in supercritical. You're thinking of it as supercritical.
Yeah. I mean, suppose we use your
model as a
for
supercritical
that.
set.
Then you may still integrate over the world sheet.
But that doesn't mean that you're integrating in the target.
Yeah. And
But in the world sheet itself, it's
Yeah,
not
sure.
clear to me what is the interpretation.
that I agree.
I mean, how to, but since there is a semi-classical limit, I mean, what is interesting is that unlike the 2D matrix models, which don't really have a semi-classical limit, here is a theory which has a semi-classical limit. So you can study things at large scale
Okay,
and
that's true.
see how does it match with your intuition.
Just from 2D gravity.
From the 2D graph. I mean, that was one of my motivations.
Is there one-point functions? Do these correlate? Do these things have one-point functions? These vertex operators?
You could have, because this normal SL to C volume doesn't, I mean, there is a divergence, sometimes it happens.
So maybe the one-point function would be your particle production, the amount of particles. And maybe the higher point functions are more subtle correlations. I mean, just free association.
Yeah, but the 1 point function is not, see, 1 point function in critical strength is 0, but here it doesn't have to be 0.
Interesting. That's great. I mean, it's very interesting.
Okay.
Yeah,
HRI
We're
questions?
asking, but
Any questions? No. I think nobody has any question. Yeah.
Everybody's hungry.
Yeah.
Okay, thank you.